Recorded is rolling. It's Thursday, August 18th, and well, here's my plan for today. I don't know how far we'll get because it's first period, but this is the period we find out. Now, last couple of days we've been reviewing trigonometry, and I gave you guys this assignment. I said on uh, this side to do three of the five, and I did two of them with you. So just had to do at least one more independently. And then on this side to pick or to do all of those. Um, and I did three of those with you guys. Let me see, quick show of hands. How many guys have finished this entire assignment, finished the entire thing? Okay, that looks like almost everybody. All right. So if you haven't turned it in yet, you guys say straight tray. You can turn it in here. Oh, yeah, let me pause this real fast. All right, recording is resumed. All right, so it looks like almost everybody's finished this. I know some of my other classes, they struggle on a little bit more, but you guys are pretty sharp in AP. So, um, yeah, here we go. Here's all the things I want to cover today, see how far you get. Now, yeah, if you guys have any questions on the trig page, I'll see if I can save like a minute or two at the end of class just to make sure that you guys are okay there. You guys are in groups, so you need to ask each other quick questions and get that. Um, this Monday and a few days from now, we're gonna have a weird schedule because there's some like new testing thing going on. Anyway, the way it's gonna work is there's going to be like a 2.5, 3 hour block for first period. And then they're gonna skip second and third and then pick up the fourth and go on from there. So I really hope that I'm not proctoring a test on Monday so that I can actually use this time period with you guys. Uh, if I get to do that, my plan is to go ahead and start you guys off with the linear motion lab and just postpone that for my other classes so I can fit in more stuff with you guys because you guys are my AP class. So that would work out. If there's a sub, if I do have to proctor, which I don't know yet because they don't have the schedule out, I'll really try to make this worth your time, whatever, however that ends up working. So uh, anyway, I hope I'm with you guys so I can do the lab with you guys. Okay, and then the Monday after that, there's a rocket launch going all the way to the moon. It doesn't have any people on it, but it's kind of cool. We're sending something to the moon, which is it doesn't happen very often. So that'll happen at 8:30 in the morning, about a week and a half from now. All right, so let's go down this list. Start with a scientific method up here. The scientific method. Scientific method. All right. So this modern scientific method goes back a few hundred years. Now, this is a process that's so ingrained in Western culture. It's just like part of how we think, right? But this was something that took like thousands of years for people to sort of formulate. And there are different versions of this depending on what textbook you open, or even depending on what problem you're trying to tackle. Sometimes you take a little bit different approaches to it. But what's kind of a generic textbook outline? What's a good first step? But even before that, you're probably asking some kind of
Observation.
yeah observation. You might say question. You might say problem. Yeah, it depends which textbook you open. Usually has one of those as like the first step. Okay. Uh, Usually good first or second step is some kind of background research because hey, it might be the case that maybe your question's been asked before, maybe a very similar question. Maybe there's already some published scientific literature out there like, oh yeah, we actually like tried this out and did like this particular experiment came to this conclusion. Uh, and I heard a bunch of guys say hypothesis. That usually goes right about here. What's a hypothesis? Yeah, educated guess is a pretty good definition. Right, I'll jot that down. Educated guess. Okay. And you're normally looking for some kind of relationship between variables, especially in class physics. It's going to be well, if I change this variable, how does this other variable respond? If you double the radius of the circle, what happens to its circumference? Should also double. What happens to its, if you double the radius, what happens to the area? Should quadruple, right? You guys saw it last week. It's like a square relationship. Okay. Somebody say something like that, like, cool, I think if I double the radius, it should quadruple the area. And then you actually make all the measurements like, hey, I'm right. Yeah. Now, very importantly, if you have a true scientific hypothesis, should a correct hypothesis be verifiable or falsifiable? and only one of those is actually true. Right? Well, let me see show of hands what you guys are thinking. Let me guys think if you have a truly correct scientific hypothesis, it should only be verifiable. Who thinks it needs to be falsifiable? Ah, all right. Class full of winners here. You guys are right. Okay. Because here's kind of the idea. If you come up with, if you couch a hypothesis in a way that it could only ever be proven correct, then when you do the experiment, oh, hey, I can only ever be correct. Well, that's not really science, right? But if you set it up in such a way that you can test somebody like, hey, I think it'll like be 9 times the area of the circle. It's like, oh, hey, it wasn't. Or I think it should double the area of the circle. And, oh, hey, actually falsified that. Right? Something you can actually disprove, something you can actually poke holes in. That's actually scientific thinking. Now, this actually goes against how our brains are structured, right? So, do you guys know the cognitive bias term called called confirmation bias? You guys know that? Right. So our brains naturally want to think more like lawyers than scientists, right? Scientific thinking is something you have to be trained to do, right? So you normally have like some idea of how things work in the world, and then your brain will actively seek information that verifies how you think things already work, and actively ignore things that might poke holes in your reasoning. So yeah, scientific thinking, you're always trying to poke holes in how you might think things work, right? And if you can't poke holes in it, then there's a pretty good chance that that's how things work. All right, let's get fourth step. You guys might think experiment. Right? So you conduct an experiment, if you have an independent variable, and then see how does that affect some kind of dependent variable. Right? Usually, especially in this class, physics, that's how things work out, right? Change this mass and see how does that affect this acceleration. What do you think comes after experiment? Data analysis. There you go. Data analysis. Okay. Now this is big, especially in this class, because this is where we're going to make a bunch of graphs, right? And then you guys already did some axis manipulation on those properties of circles last week, right? Like, hey, if I like square the radius and put that on an axis, it linearizes the graph, area versus radius squared. And then you can make some kind of conclusion. Right? Maybe you encapsulate something very nicely in formula. For example, area equals pi r squared. Right? Once you figure out, like, oh, the slope of area versus r squared is pi. Hey, area equals pi r squared. I can make that formula. You have a conclusion. Now you have a general way to know the area of any circle. If you just measure its radius, right? You can get any circle. Okay. All right, guys, good there? All right. Let's look at metric system. So we've already been working with some variables and associated units. You guys know there are two main systems for measurement out in the world, right? that have existed to present day. So just to contrast to that with like counting, you guys know that there have been different counting systems in the world. Like, why do we not use Roman numerals? Well, because you can't really do high level math for Roman numerals, but you need like a place value system. And there have been different place value systems in the world. There's been like base 5, base 8, base 12, base 60. But the world's kind of settled on base 10, right? Just somewhat arbitrarily. Maybe the aliens will visit us one day and say, oh, the rest of the universe is on base 12. Oh, you guys, base 10. But that's what we got. But then with our actual measuring systems, right, there's what comes from England, which like imperial units, but even Britain's gotten rid of this for the most part now, and they've gone metric. And the U.S., I think it's Burma and Liberia are last two countries that use like pounds and inches and feet. But one problem with like using pound, inches, and feet, the imperial system, is that you have all these like somewhat arbitrary conversion factors that have stuck around through. So like 5,280 feet in a mile. Right? Okay, well, I'm sure that has an interesting history to it, but it's not very like logical. Okay? Where does the SI stands for, like System International, it's like the International System of Units, metric system. Where does that actually originate in history? What country does this come from? Yeah, France. Boom. Yeah. All right. So, what time period? You guys think of the French Revolution. All right. Yeah, Marcus knows all the stuff, so I'm sure you guys have all learned this. French Revolution, right? So, 1770s, 1780s, there's the American Revolution. Then the French people are inspired by that, and they create their own French Revolution, which was quite choppy. But then they didn't want to just have a political reform. They also said, hey, let's reform a bunch of systems, including scientific measuring systems. And I think now's probably a good time to switch my screen and let's see, share screen. Set up. All right, sorry, I gotta connect. It's a new system, still getting used to this. Okay. Sorry for the delay here. Now, every second of class is precious. Let's try this again. Share screen, 2. There we go. Got this. Okay, where's this folder lined up? All right. Okay. So what kinds of things can we measure? Right. So there are considered to be these 7 base units in the SI system. So it's like 7 things we can measure. Okay. The top one, that red one, kg, what does that stand for? Kilogram, which could measure mass. There you go. Okay. Do you guys notice that's the only one that actually has a prefix attached to it? What is kilo? Kilo is a factor of 1,000. So 1 kilogram is 1,000 grams. Okay. And I have right here, well, if you look at watching the video from the future, it's a little tiny thumbnail. I'm holding up a 1 kilogram mass. Okay, there's a bunch of lab weights. I'm gonna pass these around class so that you guys can get a feel for like, what is 1 kilogram? Okay. All right, here, you guys can pass that around, the kilogram. Okay. So what is 1 kilogram? Do you guys know what 10 centimeters is? 10 centimeters? It's about well, about a third of your ruler. Okay. If you make a box that's 10 centimeters by 10 centimeters by 10 centimeters, you guys imagine a little tiny cube, right? I look like one of those so from the MCU. If you fill that with water, that would represent 1 kilogram of mass. Now that was the original definition. And if you do 1 centimeter by 1 centimeter by 1 centimeter, little tiny box, fill that with water. Right, that's 1 gram. So like 1,000 grams makes a kilogram. Okay. That was the original definition way back in the day, like in the 1790s. Now, in the meantime, what scientists have done over the years, and they just completed this in the last few years, is to redefine every single one of these in terms of universal constants, right? So kilograms now tied to Planck's constant. I'll give you guys a couple of examples of constants. The speed of light in the universe, 3 times 10 to the 8 meters per second. That is a universal constant. Nobody knows why that number is what it is, but it's been measured to be that. Another constant, hey, the strength of gravity, right? The Earth is so big, has a certain radial size and mass, right? You have a certain mass, right? There's an attraction between you and the Earth. Okay? Why isn't that force, whatever it is, why isn't it twice as much, or 10 times as much, or a billion times as much? Right? Well, there's something called the gravitational constant. We'll talk about in a few weeks, and it's a very tiny constant, but it's a universal constant universe. Why is it the number that it is? Nobody knows, but it's been measured. Okay, so there you go. There's kilograms. You know what else I want to say about kilograms? So this measures mass, which is like an amount of material. It's also an amount of inertia. So if you push on some number of kilograms with a force, that's going to cause it to accelerate, to like speed up. Right? That's Newton's first and second laws of motion, which we'll talk about. Okay. In the so if you have a 1 kilogram mass in space, let's say you go to the middle of space and there's just kind of floating around. Is 1 kilogram still 1 kilogram? Yep. Same amount of mass. Right? Now, sometimes that's confused with weight, which is a gravitational force that pulls down, right? Which is totally different. Right? Now, weight in the metric system is measured in, what do you think weight is measured in as a force? Newtons, right? Which you might notice is not actually on here because Newton is a composite force. I'll tell you what Newton is. 1 Newton is 1 kilogram meter per second squared. That'll make sense in a few weeks why that's the case. Right? But just to contrast that with the other system that is pretty standard in America, we usually measure mass or weight in pounds, but everything's just called pounds. So there's no really distinguishing. It's like, or you can say pounds mass and pounds force, and it gets really messy and confusing, or at least I think it does. But metric system, they do a really good job saying mass is in kilograms, weight or force is in newtons. It's 2 different concepts. Okay? Meter. So that can measure some kind of displacement, distance, length, right? Anything to do with that. The original definition of a meter, I do want to draw this out for you guys. Let me switch this over. If you look at the Earth, equator, North Pole, South Pole, and you go from the North Pole all the way down to the equator, and you divvy that into 10 billion. Yeah, I think it's 10 billion parts. You get this guy, 1 meter stick. Yeah, so you guys know this meter stick is 1 meter, right? Okay. All right, thank you. All right, so everybody had a chance to feel this thing, this 1 kilogram. All right, so that was the original definition of a meter, right? Take this distance, divide by 10 billion. Okay. Now the modern definition of meter, again, trying to tie everything back to universal constants, has to do with the distance that light would travel. Oh, the speed of light's constant, right? The distance that light travels in a tiny, tiny, tiny fraction of time, which is defined by has to do with like the vibration of a cesium atom. So let's switch back over. All right. So we got here. Right. Okay, so that's meters. Seconds could represent time, right? Now, you guys know what 1 second is, right? So if you take Earth's rotation, 24 hours, you divvy that into 24 hours, then you divvy that into 60 minutes, then divvy that into 60 seconds. Bing, presto, you have 1 second. Okay? Now, you might think, well, hang on a minute, that sure does sound like we have these random conversion factors again that I thought the metric system was getting away from. Isn't metric system based on like, we scale everything up and down by factors of 10? Right? They did try to do that with seconds. There was a brief period of time, like a few years where, and this was kind of isolated to France. They said, hey, let's get rid of 7 days a week and let's have 10 days a week. And let's do the same thing with seconds. So we'll have like, I think it was 10 hours in a day and then 10 minutes in an hour and then 10 seconds in a minute. And this metric second that was only used for a very brief period of time is actually really close to what we still use as a second. But that was just 2 year standard, and then everything just reverted back to what you know about like 24 hours in a day, blah, blah, blah. Okay. So 1 second is 1 second. So nothing really based on about that. Okay. You guys good so far? Because those three I mentioned, kilograms, meters, and seconds, that's going to carry us a long, long way in this class. For example, kilogram meter per second squared will create 1 Newton, which is a unit of force. If you do kilogram meter per second, that'd be like mass times velocity. That would be a unit of momentum. Unit of energy is just a combination of kilogram meters per second, like kilogram meter squared per second squared. So these 3 guys here is going to take us a long, long way through the semester. We're just going to keep rearranging those 3 over and over and over. Okay. Now these other 4, I might touch on a little bit here and there, but not very much in this class. Okay. So let's go over those. What do you guys think the A stands for? Good guess. Right. Ampere, yeah, which is a unit of electric current. There you go, electric current. Right. Now, since you guys are in AP, a few years ago, there was a little bit of electricity on the AP exam. They've since dropped that. I will cover that with you guys for a few days in spring semester, just so you're familiar with it. Okay, I've seen that, but we're not going to spend too long on it because it's not going to be on the AP exam at all. What do you guys think that capital K stands for?
Kelvin.
Kelvin, yes, which is a unit of temperature. There you go. Right. You could do Fahrenheit or Celsius, but you have to use Kelvin if you're ever plugging a temperature directly into an equation, because Kelvin is the only temperature system that's what. Yeah.
Relative Pascal is 0.
Right. Has 0 is absolute 0. So it's actually an absolute scale, right? Whereas like Celsius and Fahrenheit would be like relative scales that go negative, but the negative doesn't really mean negative anything. Yeah. So might touch a little bit on that with thermodynamics, but you guys know this one from chemistry, right? Mole, right? It's just a really big number. It's like, what is it, like 6 times 10 to the 23 or something like that, right? Yeah, that sounds right. What is it, 6.022, I think? All right, yeah. So 10 to the 23, that's a crazy, crazy big number. So normally it's like counting atoms sort of thing, but really it's just a number, right? It's just like counting things. And then last one, what do you guys think CD is? Candela, aha. And what does candela measure? Yeah, there you go, intensity of light. So like how bright is something? So if you want to quantify, let's say you look up at the stars at night and you're like, whoa, that star is really bright. I'm pretty sure that star is brighter than it was before. I wonder if it is exploding or some version of that. How could you quantify that? It would be candelas, right? How bright is the star? Right. Luminous intensity. There you go. Right. I do want to bring this one up to, this is an extended version of that. Okay. So here, look, on the left column, there's those 7 base SI units that we were just looking at. And then how do they relate to a bunch of other stuff? For example, volume could be cubic meters. So meter by meter by meter, right? Area, velocity, meters per second. Right? And then all these other units too, right? Yeah, Newton, the unit of force. Okay. So that's their, what's next on the list? Measuring tools. Okay, wait. There is one measuring tool that I'm short because it's being borrowed right now. So while I've got my screen switched over, here it is right here. We've got a picture of it. So let's look at this picture. Okay. Here's one way to measure mass. Actually, this is my favorite way to measure mass. So when it's available, it's being borrowed right now by somebody else. So this triple beam balance, let's just call it one of these. This works on the principle of torque. So let's look at this picture. I think you guys can figure this out. How many guys have used one of these before? These triple beam balance. Ooh, almost everybody. Nice, nice. All right, so you can put something on this plate on the left side, and then you guys see these sliders on the right side? You slide those, and you guys have all been on a seesaw as kids, right? Like a seesaw, or sometimes call it teeter totter. I don't know, maybe that's like a different regional term, but so you can like get a balancing thing going, right? So this could be. So if you slide these to the right, it provides a torque. We'll talk about torque in a few weeks, until you can balance this out, and then you can say, okay, well, what would the mass be to that, right? So you got see one that goes by 100 grams at a time, one that goes by 10 grams at a time, and this one in the front slides like one gram at a time. Right? So that's one way to measure mass. And then maybe an easier way to do it would just be to use a digital scale. Right. Let me switch the screen back over. Okay, where's Zoom? Okay, stop share. Okay, and we're back over here. All right, so here's a digital scale. You can also use to measure mass. Okay, just put something on here, measure it. Okay. Now, really, the digital scale is truly measuring a force, right? So it's like pushing down with some amount of force, and it picks up that, and it's going to translate it back to, well, what would the mass have been given that you would be at the surface of Earth? Like if you use this digital scale on the moon, is it going to give you an accurate mass reading on the moon? No, right? Do you guys think that triple beam balance would still measure the correct mass on the moon? Yeah. Yes, it would, because it works on a different principle. Okay. So there you go. Okay, so the triple beam balance would work on the moon, but this digital scale is really only calibrated for the surface of Earth. Let me make a list. We're going to make a list of measuring tools. Okay. Now, since you guys are in AP, this is especially pertinent to you guys. Here, I need to tell you guys a little bit about the AP exam. Give you guys some context with this when I talk about these measuring tools. Okay. When you guys take the AP exam is in 2 halves, pretty much halves. It's like, we have like 48, 52 or something. So one half is the multiple choice questions, and the other half, there's 5 free response questions. And out of those 5 free response questions that are scored differently, one of the ones that has most of the points, like 12 points, really big one, is experimental design. In experimental design, it's always the same format over and over and over. And I always teach this the same way, and students do really well on this part, especially for my class, which is one of the things they always ask. They'll always ask you like some prompt, like, suppose you had this or that scenario. How would you design an experiment to go about determining blah, 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 right? For example, yesterday, one of the stories I took you guys through is like, hey, what if you have a pendulum of some length or like different length pendulums, and you time it and you can figure out what gravity field is on the planet that you're on because it'll swing differently on different planets, right? So then you would say, oh, well, I would set up this table, I get these length pendulums, they measure these time periods, and I would manipulate this way and then linearize this graph. Okay. So one of the parts is always listing your measuring tools to say what quantities you're going to measure. And there's only a small handful of options that are ever available. Look through my notes. I got them here, so make sure I don't miss one. Okay. What do you think you're going to, look, here, maybe I'll just this way. Variable, I'm gonna make a table. Unit and measuring tool. Okay. So I'll go in order by my notes I have right here off camera. Uh, let's say some kind of displacement. What's the unit for displacement? Meter. And what's a good measuring tool? Ruler works. What else works?
Meter stick.
Meter stick. Okay, so different lengths. One might be better than the other depending on what you're trying to measure. So there you go. So that'll cover that. How about an angle? What do you measure angle in? I heard degrees and radians. Those are both good. I'm going to say degrees. I'll put radians on here too. But more often we're going to do degrees in this class. I guess that's a similar idea with x. You could do like centimeters or something, meter centimeter. And then what are you guys going to use to measure angle? Protractor. Yeah, and since it has degrees on it, then use that more often. Right, how about how do you guys think you're going to measure time? In seconds with a stopwatch. Oh yeah, stopwatch. And actually, I'm going to have you guys use your cell phones whenever there's a lab where you have to measure time. Okay, because cell phones charge. Okay. How about ooh? Do you guys think that there's a way to directly measure what's that stand for again? The lowercase v? Velocity. So this could be velocity or speed. And that would be in what unit do you think? Yeah, meters per second is a good unit. Could be centimeters per second, something. Okay. Now the school has some new equipment over the summer. Yeah, so we have a whole box of these. These things are like $50 or $60 each. So I was really excited to get a whole set of these. And I have one of them here. I'll show you guys. All right, so turn this thing on. Okay. Okay. If you click both these buttons, it'll clear it out. Okay. Now there's a unit here. Right now it says meters per second. If I choose the select button, it will. Oh, what is it doing? Well, it didn't do that before. Before it changed the unit for me. Okay, what's going on? Try to clear this out. Okay, well, that turned it off. All right. Okay. I think it's gonna work. All right. Now, just to show you guys how this works. Okay. Now, if you want a speed, do you think you need like 2 points and a time to go from point A to point B? Right. So I'd say two dots here, like two sensors. And if I run something through this, I didn't do it. Look at that. 2.42 meters per second. 2.42 meters per second. Okay, let me try again. Let's clear that out. Okay. And run my pen through. That didn't work. 3.82 meters per second. Yeah. All right, so that is a new tool we get to use that haven't had in the past. I'm excited to have you guys try this out here pretty soon. So that could be, you could use, sometimes it's called a motion detector. Is that what this is? It might go by some other names too, but I've seen AP use that term specifically. So if they're like rating by some rubric, that might be the term we're looking for. All right, how about, mass we talked about? This could be in, kilogram is the base unit, right? Because kilogram is like baked into, it's like an ingredient of like the higher level composite units, like 1 Newton is 1 kilogram meter per second squared. Now, if you're coming from chemistry, you might say, well, what about like grams or something? Right? I guess you could measure that too. Like this guy here is 200 grams or 0.2 kilograms. Okay? You could say a scale. You could say a triple beam balance. Okay? I guess, yeah, or a digital scale would work. Anything like that. What else could you measure? How about force? Do you think you can measure force with something? Right. Now this is going to be in newtons. Right now, Newton is a composite unit. I should tell you guys this. 1 Newton is equal to 1 kilogram meter per second squared. Okay. And one tool you could use to measure that would be a force probe. AP likes that term. In this class, more often get to use these spring scales. spring scales, okay? Or just spring scale, I guess if it's singular. Okay. Do you guys see right here it says N for Newton? Look, it's scale. Now there are different spring scales that have different stiffness springs. So this is kind of a medium one. Okay. But let's say I take this 200 gram mass. I'll tell you guys, 200 grams weighs almost 2 newtons, almost 2 newtons of gravity force. It's a little bit shy of that, but I'll round it to about 2 newtons. So if I hang this, do you think there's like 2 newtons of gravity force? Okay, now let me stop the scale exactly where it is and turn it so you can see the camera. Look at that. It's right at the 2 Newton mark. All right. Now, if you turn this around, rotate it, it says grams. Now, grams is actually a mass, right? So the grams only works if you're on what planet? Earth. If I take this up to the moon, it's going to give me the correct number of grams? No, right? But it will tell me the correct force because that's actually what this director measures is force. Okay, it's like the equivalent mass that would give you that force. Okay, because it's pulling on the spring with some force to make it stretch that amount. Right? Okay. In fact, the more you stretch the spring, the more the spring pulls back, and that's a linear relationship that's called Hooke's law. Right? That's why it'll stop at the correct number of newtons of force. Okay. All right. And I'm going to throw one. Actually, that's all you need for your own AP exam. Right. So when you guys get to the experimental design question, which is 12 points, which is like a good third of the way to passing the entire exam, if you get every single point right on this particular question, that's all your possible measuring tools to pick from. Right. That's it. That's all the quantities you could possibly measure in this class and what you could use to measure it with. Now I'm going to throw one more in here just for completion. And that's if you want to measure either current in amps or voltage or like potential difference in volts. Okay. And now those are two different quantities. They're two different ideas, but you can use the multimeter to measure the, actually I should say you can use an ammeter function to measure current, and you can use a voltmeter to measure potential difference or voltage. And this is what a multimeter looks like. And then you turn this toggle to measure either voltage or current. Okay. And then hook up your leads and to some circuit. Okay. All right. So you guys good on measuring tools? Yeah. Those are capital V's. Yes. Yeah. Thank you. Good call. Yeah. Yeah. And the triangle's like delta, which is like a difference in this case, like potential difference. Okay. Volts is the only one where the unit and the variable are the same letter. All these other ones that they're different. So I don't know if that's working here. Sometimes you use like lowercase epsilon, but same thing. All right, there you go. All right. So next on my list is prefixes and orders of magnitude. All right, no, hold on. No, sorry, just swap my notes. Let's do scientific notation first. Scientific notation. All right, so suppose you have, let's go with the mass of the Earth. Anybody know what the mass of the Earth is? How about kilograms? Oh yeah. Okay. So here's 1 kilogram. If you had this many kilograms, you would have the Earth. Yay. Now, do you guys think you're going to have to do some calculations that involve the mass of the Earth? Yeah. I bet if you want to know how fast you have to get satellites to orbit the Earth, that might be a number that's involved in those calculations, right? Like orbital speed. Okay. Now, do you think it take a long time to plug that into the calculator? And you don't want to like miss one of these zeros, like, oh, okay. Also, are these zeros here even significant? No, they're just placeholders, right? Like, I don't really know they're actually zeros. It's probably like 1654870. Who knows, right? So how many digits are actually significant in that number? Yeah, probably just those 3, and the rest are just placeholders, right? Okay. So there's a much more efficient way to write this number, which is what? Exactly. Nailed it. Yeah. Okay. So if you go from this point to put the decimal so there's just a number in the units place. Yeah, that's 24 places you have to shift it. Okay, so that'd be like times 10 to the 24 to restore the number. Okay. Yeah, and you guys are right. That does have 3 significant digits. Okay. Hey, what if I do this? What if I throw a 0 right here? Would that digit now be significant?
Yes.
Yes. Right. See, the way I wrote it in the expanded version, it's ambiguous, so you assume that it's not. But if I specifically put a 0 here, now you know that, okay, I do know that level. It definitely is that number, which it's not in this case. I'm just using that as an example. But if I did put a 0 there, you'd have 4 significant figures. Okay? But 5.97, you have 3 significant figures. Okay. How about this? What if you have, let's look at that universal gravity constant that I referenced earlier. Right? Now, nobody knows why this number is what it is, but there's some gravitational attraction between the moon and the Earth, and Apple and the Earth, you and the Earth and the sun, right? And it's related to this number. Okay, so same problems as before, except that now it's a tiny, tiny number, right? How can you write this in scientific notation? Exactly. There you go. Boom, like that. Okay, so guys, negative powers, does that make the number negative? No, that's just that you think like fraction or removes the decimal the opposite way. Okay. Okay. You guys good with scientific notation? Okay. So it's always times 10 to the something, right? And then that power will tell you how far to move the decimal. To the right if it's positive, to the left if it's negative. Okay. Okay. Now let's talk about some prefixes. Prefixes. So I bet you guys know some of these. I'm gonna list a handful that are you'll see more often than not in this class. Okay. If you see, here, let's start from like a base, for example, like meters, for example, meters. You could have seconds, grams, or something like that, right? What if you have, what if you see a prefix K, like as in like kilometers, kilograms? That's a factor of a what? 1,000, which is 10 to the power of 3. Right? What if you, and that's a lowercase k, right? What if you see a capital M? Yeah, that's mega. I should spell these out. So kilo, mega, okay. And that would be mega's a million, which is like 10 to the 6. Okay. Hey, you guys know if you have a computer file that's like 1,000 kilobytes, it rolls over to like a megabyte. It should tell you guys that computer files technically is a factor of 1024, but you guys get data, right? Okay. And what if you have like 1,000 megabytes that rolls over to 1 gigabyte? Giga, capital G, as a prefix, could be a factor of a billion. A billion, 10 to the 9. Right. And what's 1,000 billions?
A terabyte.
Tera. There you go. So the next one would be tera. I don't know if I've ever seen that show up in this class, but that's what it would be, capital T for tera. Right. What if you go small? So what if you have lowercase m? For example, mm could be millimeter. Right? Is that like
1,000?
Yeah, 1,000, right? Which is like 10 to the what? -3. Yeah. What if you see this? This is the Greek letter mu. Looks like a U with the tail on it. Yeah, micro. Oops, I meant to write this. Milli, micro. Right, as in like micrometer could work. Microgram. Right, something like that. You guys think that's 1/1,000,000? 1 billion. Right, micro, small. Oh, interesting. So mega is a million or something. Micro is 1 million. Oh, what's 1/1,000th of that? Nano. Yeah, nano. You guys ever heard nanotechnology? Nanobots. You think it's order of magnitude like a nanometer? Okay. So it's 1/1 billion, which is 10 to the negative 9. Okay, those aren't all the prefixes. Well, let's get centi, right? Like centi could be 1/100, right? 100 something a dollar, 100 centimeters in a meter, right? So there are some other ones, but it's more often than not, you'll tend to see those prefixes in this class. Questions so far? There. All right. Okay, let's do this. I think it could fit in precision and accuracy. And then there's a lot I want to talk about dimensional analysis. Dimensional analysis is a really handy tool, but that I'm going to save for tomorrow. But I do want to tell you guys about precision versus accuracy. So let me switch the screen back. All right. Some of you guys might know this difference. If you don't, then well, that's why you're at school to learn stuff. There's a good dartboard analogy here to help you see what's the difference between those two terms. Okay. Now, so suppose maybe you design some machine and it's going to be a dart throwing machine, right? And if your dart throwing machine, all the darts are hitting your target right in the middle, like that top left quadrant. Okay, well that would be both precise and accurate. Great, you're winning over and over. What if your machine is hitting the same spot over? I'm looking at the top right quadrant. What if your machine is hitting the same spot over and over and over, but it's not the intended target? That would be very what, but not very what. Yeah, precise but not accurate, right? Okay, so this top right dart throw machine has a lot of precision, but not very much accuracy. Right? So you have to like recalibrate it, and then it could probably go after you recalibrate it. Right? What if you come up with a machine, you design a machine that like on average it's the central target, but it's kind of spread all over the place. Okay, so that you could call that accurate, but not very precise. Okay? And if you have neither, that's like that bottom right quadrant. Okay? You guys okay on that? Okay. Now that's one version of precision versus accuracy. Let me show you guys a little bit more tangible example of that. We'll switch back over here. Like what does that have to do with? Because all these measuring tools that we've gone over here, all these measuring tools are going to have a little bit of error built into them. Like for example, with stopwatch, if you time it. So how does that precision and accuracy translate to like these measuring tools? Okay. Well, so we got. I draw a table up here. Suppose there are different manufacturers of different scales, say different types of scales. Okay? And let's say there are two kinds of scales. The measurer 4,000 and the knower 5,000. That bigger number. And we pick a 3 of each of those scales. So let's say scale sample. Sample. Okay. So go scale A, scale B, scale C, and then scale D, scale E, and scale F. Okay. So this right here might be scale A, for example. Okay. And we've got 6 different scales, 3 of one kind, 3 of the other kind. Okay. And then we're going to take, let's say this lab mass right here. Now this is has a number printed on it. It says 500 grams. So it's like 0.5 kilograms. So half a kilogram. Okay, I'm going to put this on every single one of these scales. Okay. And it's going to give me a number. So what's the reading on each scale? Okay. So say scale A says that's 499 grams. And then scale B says, no, that's 502 grams. Scale C says 504 grams. Okay. And then what about the knower? Let's say the knower says it's 501.917 grams. Is that scale D? And scale E says, no, it's 501.913 grams. And scale F says, no, you're both wrong. It's actually 501.920 grams. Okay. All right. So which scale, the measurer or the knower, is more precise, has a lot more precision? The knower. This guy's way more precise. Say more precision. Okay. So the more decimal places you have, the more precise it is, right? Which of these scales is the most accurate scale, do you think? Well, that's maybe a trick question. So like what's the true value of whatever weight reading you do? Like how do you know that what if like the true value that like only God could ever know if God comes down like, the actual value was 503.9976, right? So you say, oh, okay, well that one would be the most accurate in that case, right? So who's the most accurate? Well, kind of a hard question to answer because who knows what the true value is? All you can do is like measure it in many different ways. Like maybe take the average or something. Okay. Okay. Any questions? Anything today? All right. So that's going to be after my pause point. Tomorrow we're going to do a bunch of dimensional analysis, and then I hope I'm here for Monday so I can do a lab with you guys because that would be a really good use of Monday. All right. But I'm going to stop this recording here and then answer any questions you have about that trigonometry page.